This is my solution to problem 15p.71. The question reads as follows. A thin, hollow, spherical plastic shell of radius r carries a uniformly distributed negative charge, negative q. A slice through the plastic shell is shown in figure 15.94, which is the diagram that you see here. To the left of the spherical shell are four charges packed closely together as shown. The distance s is shown greatly enlarged for clarity. The distance from the center of the four charges to the center of the plastic shell is L, which is much larger than S. Remember that a uniformly charged sphere makes an electric field as though all the charge were concentrated at the center of the sphere. So, the first step would be to draw the diagram, which is on the page, but I drew it again here, a little bit larger. So the first question asks, calculate the x and y components of the electric field at location B, which is here a distance small b to the right of the shell. Explain briefly, including showing the electric field in the diagram. Your results should not contain any symbols other than RQ, Q, S, L, B. You need not simplify the final algebraic results. So, one thing we need to remember is that electric field flows from positive to negative. So here is an example of a simple dipole electric field. And since this problem has four charges in this arrangement, we can make the assumption that it will act as two dipoles. One will be horizontal and one will be vertical. So using that, we have specific formulas that we need to remember. The first one is the electric field for a point charge, and we can remember that since this plastic shell has charge negative Q, and the point B, which we're calculating the electric field at, is outside the shell, it can be simplified to be considered a point charge at the center of the sphere. So this is the formula for that. The next one is for the electric field of a dipole where the point we're calculating is on the axis, and the next one is for a point that's perpendicular to the axis. So using these formulas, we'll calculate the x and y components of the electric field. So we know that the orientation of the four charges can be modeled by two dipoles, which I stated earlier. So we take into account dipole 1, which is the vertical dipole. So I've drawn a simple representation of the electric field due to this dipole at point B. We can see that the electric field at point B is pointing downwards, so based on the diagram, we know that the electric field due to dipole 1 at point B is in the negative y direction. So we know direction. Next is to find magnitude. For this, we use the E dipole where B is perpendicular to the dipole axis. As we can see here, it's located perpendicular to the axis. So, using this formula, we can find the magnitude of that force. We know that R is equal to L plus R plus B. As we can see here, L plus R plus B is the distance to B. So, plugging in those numbers and the direction, we get this as the electric dipole perpendicular. Next electric field we need to calculate is due to dipole 2, which is the horizontal dipole that is on axis with B. Here is another simple diagram of the dipole at point B, so we can see that it points in the positive x direction. So the electric field due to dipole 2 is in the positive x direction. So we have direction, next we need to find magnitude. We use the formula we stated earlier, E dipole on axis, since B is located on the axis of each component of the dipole. We use this formula, where R also equals L plus R plus B, as we can see in the last problem, which gives you this as the dipole for on axis. The next, we need to consider the plastic sphere. Here we can see that point B is located outside of the sphere, so the sphere can be considered as a point charge at the center. So we know that since it has a negative charge, the electric field is going to point towards that negative charge. So from B, it's going to point towards the center of the sphere. So that is in the negative x direction. So the electric field due to the sphere is in the negative x direction. Next, we use the formula we stated before, which is the electric field for a point charge. And R in this problem is R plus B. As we can see, the center of the sphere is located at the point, and to get to B, it's a distance big R plus little b. So this is what we get from that. The next and final step of this part of the problem is to sum all of the previous electric fields. So I factored out 1 over 4 pi epsilon naught from each one, and then using the directions I added all of the electric fields, and this is what you're left with, and it's in newtons per coulomb. Part B asks what simplifying assumptions did you have to make in part A. So the simplifying assumptions I made are that the shell acts as a point charge at the center of the sphere. So at a point in the center, it'll act as a point charge, which helps us to use this formula rather than something more complicated. And also, the dipoles cause no movement of charge in the sphere. So there is no induction of charges due to the dipole in that sphere itself. So part C of the question says that the plastic shell is removed and replaced by an uncharged metal ball. At location A inside the metal ball, distance B to the left of the outer surface of the ball, accurately draw and label the electric field E ball due to the ball charges and the electric field E4 of the 4 charges. So, first thing we need to do, we need to draw the new diagram, which is essentially the same except there's no point to the right of the sphere. So, using the previous diagrams, such as this dipole diagram and this dipole diagram, we can figure out which direction that the electric field will point due to the two dipoles. Essentially, it's the same problem. We're using a point A because the dipoles will act on the center of the sphere. So it's essentially the same as the last problem. The distances just change slightly. So using those two diagrams, we get a force in the negative y direction and a force in the positive x direction, which leaves us getting this field for E4. Due to this field, we will get a reaction field in the ball, which is equal and opposite, so we see that the electric field due to the ball is in the opposite direction. This is caused by an induced charge in the ball, because we know that the electric field points towards a negative charge, and since we're in a metal sphere, the electrons are mobile, so the electrons will move in the opposite direction of the electric field towards the top of the ball, which we can see here, leaving the bottom with the residual positive charge. So we can see that the reactive electric field will be in the opposite direction and will cause this charge distribution, which is part D. Show the distribution of the ball charges, which is there. Next is calculate the x and y components of the net electric field at location A. So we can see the two electric fields acting on point A, and as I said before, they are equal and opposite due to induced charges in the ball. So the total electric field will be 0 newtons per coulomb, which is due to the cancellation of the field due to the induction of the electric field in the sphere. So that's my solution to problem 15P.71.